Thanks everybody for joining for the Cape Ann Geology with Kate Murdock. We're going to try and start right at 7, which is another minute or so. So thanks for your patience. I know Kate is on a tight schedule today. We're lucky to have her. We thought we were going to have to record this and make it a recorded viewing tonight, but she did manage to pull this off here in person. But if we don't get all of our questions answered, I'm going to remind people to email me and I will get your questions answered. So in terms of introducing Kate, I just printed this off, thank goodness. Look all around us here in Cape Ann. We see many different types of rocks and stones. The geology of the area stretches back millions of years here on the east coast of the US, including Cape Ann. So join Kate Murdock, consulting geologist, talk about the physical and geological history of our local area. So again, thank you, Kate, for coming. Just a quick housekeeping note for people. If you would kindly mute yourself. If you have a question, put it in the chat or wait till the end, whichever you prefer. But if people can keep themselves muted during the show, this keeps things like crashing dishes or barking dogs or yelling spouses to a minimum. So again,
we're screaming 2-year-olds.
And screaming 2-year-olds. Thank you for that reminder. So I'm going to turn things over to the lovely Kate Murdock, and thanks everybody for coming.
Thanks, Dana.
You bet.
So thank you all for coming. And like Dana said, I am more than happy to answer any questions that you have. I do unfortunately have a super tight schedule this evening. My supervisor is already texting me about when I can have a phone call with him. So that's the life of a consulting geologist. Anyways, if I don't get to your question today, by all means, send Dana your questions. I'm more than happy to answer them. And I'm just happy that you're all here. So let's begin. Now, first and foremost, Cape Ann geology is, for a geologist like myself, I am a rock magnetist by trade. I essentially do magnetic mineralogy. This is really kind of interesting stuff for geologists, but if you kind of look online to see if there's anything that, you know, a non-geologist can look at to tell you a little bit about the area, it's very sparse and it's really, really technical. So I'm trying to give you a kind of a broad picture of what was going on with Cape Ann geology. And really, this is a story of 2 events or 2 times within the Earth history when we're looking at Cape Ann geology. We're looking at the formation of the rocks and then how the rocks look the way that they do today. And we'll see if this will actually work. There we go. So I love this map. This is one of my favorite maps of Cape Ann, and this is a map, this is a geologic map of Cape Ann from 1887. And it looks like there's nothing on here, but it's actually really rather fun for 2 reasons. One, you actually have the topography, so you can see what the old topography looked at. All these lines are contour lines, so you can see kind of these linear features like this. We'll talk about what those are in a second. But you also see this kind of darker gray area, and then the rest is all this tan color. Well, that darker gray area is one type of rock, and then in 1887, they lumped this other type of rock all together. We have a little bit of a better understanding, you know, 140 years later, but this is a really great map to look at. This is not typical of what you see across the country. Well, certainly not across the country, but not even within New England. You don't see maps of this detail or of this importance in the 1800s, because really geology was just getting started as a science. Prior to that, you know, geology was used. If you ever go down to Saugus Iron Works, they had to have a knowledge of geology in order to get the iron that they needed out of the rocks, and they knew where to get the calcium from as well, from a different type of rock. So you did actually have geology going back thousands and thousands of years, but really it was a trade. You had to know the landscape. It was not considered really scientific. It was just something that you had to know in order to make your business work. So this is when you start seeing geology kind of take off as a science. So, like I said, Cape Ann is a tale of 2 times, really. The beginning of what became Capan and then why it looks the way that it does. And really to kind of give you a good idea of when it started, we have to go back about 900 million years to a supercontinent named Rudinia. Now, if you've heard the term supercontinent before, you typically hear of Pangaea. That's usually what we talk about, but that's actually only one supercontinent in the Earth history of supercontinents. We have the supercontinent cycle where we go into the supercontinent like Pangaea, everything breaks apart like it has today. So you have different smaller continents. It will eventually go back together and it kind of breaks apart, comes back together, breaks apart, comes back together. And the one that is where we really started was Rodinia. And just to give you an idea of where Rockport would be, this is Laurentia. This is actually the original kind of terrain that became North America. We would be approximately down here at one point. Now, to put this in perspective, I'm talking about 900 million years ago. Where do we even land as far as that's concerned? And it's actually fairly recent. So this is about 1 million years, excuse me, the 1 billion years ago is about here, the Neoproterozoic. So we're talking about the beginning of Capan starting into the Neoproterozoic era. And as you can see, this is not that long ago in the geologic time, but as far as what we think of as geologic history, it's a really long time ago. Again, different way of different perspective. We have, oh, excuse me. We have the Hadean time period. This is the Hadean eon, where it was just essentially a magma ocean of the Earth from 4.6 billion years to about 4 billion years. We have the Archean era. This is the oldest rock that we were able to identify is from the beginning of the Archean era. At the about 3.8 billion years ago, that's the first life signs that we were able to see in the oldest fossils. These are like stromatolites, so these are bacterial colonies. At about 2.2 billion years ago, that's when oxygen went into the atmosphere. And then we start seeing things like eukaryotes. This is our first plant that photosynthetic plant that was showed up that was able to put oxygen in the atmosphere. And then we start seeing multicellular creatures about 600 to 800 million years ago. So this is about the same time as Rudinia. So this is really the time frame that we're talking about. It was like we're just getting into multicellular creatures at that point, which is fairly recent. Again, another perspective when we're talking about Rudinia, we're talking about this area here. The rest of our history in Capan really starts going on in the Ordovician, Silurian, and the Devonian here. This is when we start seeing cephalopods and corals and sharks, but not necessarily the way that we know them. And trees, land trees, did not even exist at the point that the rocks that formed Capan. So that is in the future. So just to give you an idea of what we're talking about. So, excuse me. So if we think about Rudinia, that's about 900 million years ago. It was a supercontinent and it started breaking up about 600 to 850. There's a little bit of question about when it started breaking up, but we're talking about really kind of getting going with breaking up about 600 million years ago. And the supercontinent is actually all the way around the edge. It starts breaking up and you can see pieces kind of coming off, becoming microcontinents or smaller continents through time. And this goes on until you start seeing terrains kind of show up. So we have smaller pieces that have come off of Laurentia, and you can see that they're actually starting to move towards each other. And this is the first, what we call mountain building event is called an orogeny. So this is an orogenic event that happens, and this is when we start seeing things come together, like right here. And this is the tectonic orogeny. So this is the first mountain building event that would eventually turn into the Appalachians. And you can see the mountains have started forming here. So this is where we see a lot of the southern Appalachians that have formed from part of this mountain building event. And it continues on. Rudinia continues to break up and start breaking apart into smaller and smaller pieces. And eventually it will start coming back together. So we keep moving on. We have these smaller pieces coming together until we get to what is Pangaea. So let me just show you one other thing that I kind of lost here. So about 350 million years ago, this is another terrain. I will talk about it in a second, but it's called the Avalonia. So if you've ever heard the Avalon terrain, when you're talking about Capan, this is a small island arc chain that collided with the northern part of the Appalachian, what is the Appalachians now. And so that's another orogeny that happened after the tectonic orogeny. So we're talking about the Ordovician time period at that point. And then we get Pangaea. And at that point, we have Massachusetts that's near the equator. So it was a lovely palm tree tropical paradise at that point in time. And it eventually broke apart as well. So starting about 200 million years ago and going until today, Pangaea has broken apart and going farther and farther away into a more recognizable continental system. So this is no longer a supercontinent. This is our smaller continental systems. So I just also want to point out, this is what it looks like present day. 21,000 years ago, I just want you to notice that we had an ice sheet over here. That's actually the second part of the story, but this is what we have today. To put this into a different perspective, this is actually a great little website that was shared on Popular Mechanics, and it was find your home at different points in time, at geologic time. So you can actually go and put in your address. You don't really need to put in your address. You can literally just put in Boston, Massachusetts, and it will get you about the same location. But it shows you where it has moved over the course of the Earth history going back 750 million years. So this is what it looks like today. And we can see that here's Massachusetts right here. And this is, as it goes through time, you can see that it is not even close to where we are today. And there was an ocean in the middle of the US about 100 million years ago. It continued to move away. This is where we had Pangaea. So Massachusetts is down here, closer to the equator, tropical paradise. A little bit farther, it's even right on the equator. And it's over essentially in the hemisphere that Africa and India are in, like in that area. And it keeps kind of going south. So about 450 million years ago, we were in the southern hemisphere. This part of the geology was in the southern hemisphere. And by about 600 million years ago, it was on the southern pole, and 750 million years ago, it didn't even exist. There were no rocks that are on Capan that were around 750 million years ago. So a different perspective, just to kind of give you an idea. This is actually the southern pole. It flips it upside down, but this is the southern pole. And that was where we were 600 million years ago. This is a better perspective. And you can follow where we were through time. So essentially, we have been all over the Earth. The rocks that are here currently in Capan have been all over the Earth during their existence. Now, to put this just kind of in perspective to make it a little bit easier to understand what's going on, this is Rudinia, the supercontinent. It started rifting apart, so it started pulling apart, and you had what we call a passive margin for a little while. This is when you don't have any activity. It's like what it is now. We have a passive margin. You can think of an active margin as like California. Lots of earthquakes. You have volcanoes in Oregon and Washington. That's an active margin. We have a passive margin. We have nice beaches and not much else. You know, we have to worry about hurricanes and nor'easters, but we don't have to worry about a lot of earthquakes and volcanoes. And you can see that we had a passive margin here, but there was a small microcontinent that was coming in and eventually sutured itself onto what was left of Rudinia. This is Laurentia. And it sutured itself onto through a collision. This is the beginning of the Appalachians. We had some volcanism that was going on. This is Avalon. This is what makes up the majority of Capan at this point. You have this other microcontinent that smashes into Laurentia and what was the tectonic orogeny. And so we have more mountain building. This is, excuse me, my mouse doesn't want to work today. And then it says Africa here, but this is actually another more minor supercontinent. This is called Gondwana Land. It was actually a combination of Australia, Africa, and India. It smashed in as well, and this is what became Pangaea, all of the continents together. And that's really where we have the Appalachians that came from. Once Pangaea started breaking apart, that's when you start seeing the Atlantic Ocean open up, and we have present day with our coastal plain. So we have a combination of rocks from all over the world, but from the Taconic orogeny, the Acadian orogeny, where Avalon got sutured on, and also the Alleghenian orogeny that was just before Pangaea. So we're talking about several mountain building events that created the Appalachians, created the terrain that we're sitting on right now. Just to throw in a tidbit of information with that, the Appalachians, during their height, about this Alleghenian orogeny, were about twice the size of the Himalayas. So we're talking about a huge, huge mountain system. And it's one of the, if not the oldest, the most ancient mountain systems still in existence. So if you ever go to the West Coast, they're like, oh, you don't really have mountains on the East Coast. Well, that's true. They're not nearly as big as the Rockies are now, but they used to dwarf the Rockies. This was such a large mountain system that it dwarfs anything that is in existence today. It won't always be that way, but that's how it was. So if you think about, you have such large mountains, what happened to them? That we don't have those large mountains anymore. And that is just essentially what wind and water does over 250 million years. That's the power of wind and water. So we think of like volcanoes and earthquakes and all of these earth processes being so incredible and building so much up, which they do, but wind and water do just as much to break them down. So after that whole wonderful story about all the mountain building events, this is a geologic map of Capan. So just kind of put this in perspective a little bit. We have Stage Fort Park actually right over here. And I mentioned that specifically because you can barely see this line that's going through Capan. It's where they're doing a cross section. So I just want to point that out. So we have Stage Fort Park over here, and then we have some of the other features that we have going on. Oh, I thought I had marked it. I have a couple other pictures to show you of things like Pigeon Cove and other areas around the Capan. Sorry, I didn't actually mark it on here, but that's neither here nor there. The thing to take from this particular map is that you can see a whole lot of pink, and all of this pink is what we call the Cape Ann complex. So this is all granites, sort of. And the yellow here, that's in the middle, this is the Squam granite, which has a slightly different history. It's a little bit older than the Cape Ann granites. And then you have the red, that a couple of little blips of red and everything. That's actually the Salem gabbro diorite. And it's not very common in Cape Ann, but when you get down to Salem and Lynn, that's the majority of the rock there. But what's interesting is that the Squam granite and the Salem gabbro diorite predate the Cape Ann granites slightly. So they started forming about the same period of time, but the Salem gabbro diorite does predate it slightly. So why is this important? Well, this is, like I said, this is Stage Fort Park here. This is the cross section that we're going to look at. So essentially, we're going to take a slice through Cape Ann and see what it looks like if we were looking at it. So like, think of it like cutting through a cake. You can kind of draw that line, you cut through it, and you want to look at the layers of the cake. And this is what you see. And I apologize about the colors here because I was looking through this and I realized that they didn't use the same colors. This is a USGS map, and this absolutely drives me crazy when they don't use the same colors for the cross sections. And I looked at this for like half an hour today, and I was like, they messed up. They used the wrong colors. They have the wrong rocks here. It looks like they move. It's just a geologist thing. It's nitpicky, but anyways, majority wise, it's actually a great thing to show you. Here's Gloucester Harbor here. Here's the shoreline. This is actually where Stage Fort Park is, and it's right square into an alkali feldspar granite. So if you're talking about tablet rock in Stage Fort Park, it's actually this particular rock right here. It's an alkali feldspar granite. So it's a very common granite. It's very indicative of the area. And that's typically what you see. This red here, this is Salem gabbro diorite. This is the orange is the squam granite above it, and then you can see the Capan granite all around it. I say that this is really interesting because the Salem gabbro diorite barely predates the Capan granite. And so what you typically see is when one rock predates another, you typically have the younger rock intruding into the older rock. So what we should typically see is kind of like a blob kind of moving into the a blob of the Capan granite moving into a blob of the Salem gabbro diorite, but it's not quite what we see going on here. It's a little bit more complex, a little bit more messy, but you can see that we have little bits of the squam granite into the Capan granite. We have some bits of the Salem gabbro diorite and the squam granite. This is how we tell what was there beforehand. You can't have something intruding to something that's not there. So this Salem gabbro diorite was first, and the squam granite came next. It actually looks like it formed around it, and then the Capan granite seems to have formed around that, which is just geologically interesting. It's not normal that we see that. This is just another perspective, just to kind of give you a better idea. This is Boston down here. This is a kind of blowing back and looking a little bit farther. Capan's up here. Salem Neck is here. So this darker gray color, this is the Salem gabbro diorite. This OSGR up here, this lighter gray color, this is the Capan granite. So you can see that they kind of like interfinger with each other. They're all about the same age. And this is all from when the Avalonian terrain crashed into what was Laurentia, a smaller supercontinent about that time. And here's a little bit more of a close-up, and you can see again, all of these blobs just kind of mixing together. By the way, if you're wondering what all of these dashed lines are, those are fault lines. Do not need to worry about them being fault lines like what you see in California. They are not active currently. They are not going to run under your house and cause all kinds of issues. This is when you had essentially all of that rock scrooching together, and it would break apart along these fault lines. And this is essentially thrust faults going over the area. It's very common to see. They have not been active in a very long time. And people typically ask me, well, could they become active again? And the answer is yes. If you had the right forces moving on them, yes, they could become active again. Is that likely to happen in our lifetime? No. But if you're wondering why there are earthquakes from time to time around Capan, north of it, east of it, south of it, it's because you have a fairly complex history that has a lot of fracture networks that are still there. Fault lines and fractures never fix themselves. They're not like your skin, that you don't get a break in your skin and it heals. That's not how the Earth's crust works. Once it's broken, it's always broken. It will always be a weak point. So when we do have earthquakes, they're usually related to one of these ancient fault lines. There's a little bit of a pressure on that. It could still be from rebound from the glaciers. The glaciers are only about 10,000 years ago, so that's still relatively recent in geologic terms. And so you get little earthquakes here and there, but nothing like what we see in the West Coast. So what kind of rocks do you actually go out? If you were to go out your door and look in Capan, what kind of rocks would you see? Well, the Capan granite complex is typically what you would see, and it looks mostly like this gray one up here. This is actually from Capan. You would not believe how hard it is to find actual pictures of like rocks. People are not very easy to get pictures of rocks online to add to these things. And the pictures I have are like real close up, so bear with me for that. This is the Capan granite complex. This is very indicative of what it typically looks like. It's a gray colored rock. It has alkali feldspar, pelagic clay feldspar, hornblende, and quartz in it. The other type of rock that you see that's fairly prevalent is a Capan syenite, which is equivalent to what we call the Beverly syenite. So syenite is S-Y-E-N-I-T-E, in case you're wondering. What is a syenite? It's the same thing as granite, except there's no quartz. So you can actually go out, and I can tell you right now, I can teach you how to identify a granite from a syenite right now. It will take 30 seconds. You just have to look for quartz. And how do you know if you found quartz? Well, if you pick up a rock and you see this kind of dark gray, kind of clear mineral in your rock that doesn't reflect light very well, but you can kind of see through it, that's quartz. When you look at syenite, you can possibly see through some of these pieces, but they all reflect light. If you kind of move them around, they will reflect light, and it's because it's reflecting off of a cleavage plane. Quartz does not have cleavage planes. So you can hold up a piece of rock and look at it and be like, oh, I don't really see much light reflecting off of this. I can kind of see through this mineral. Quartz. If you look at another rock and it doesn't seem like you can see any places that aren't reflecting light, it's a syenite. Typically also the barely syenite is pink. Another kind of telltale way to tell that you have a syenite, at least in this area. It's not universally true, but at least for here, we can say that. So these two rocks are the typical ones that you tend to see in Capan. This one is a picture of a Salem gabbro diorite. It is dark colored, has this kind of a greenish color. I have seen pieces that are almost white and black, kind of like a Dalmatian as well. That's more the diorite spectrum, but that's typically all we see in Salem. I don't typically see it outside of Salem. So you can find this in very rare places, but these are the two typical ones that you see. So what does it all tell you? Well, here's your little mineralogy information for the day. The lighter the color of the rock, the more felsic it is. The more felsic it is, that means the more quartz and silica that you have in the rock. Why is that important? Well, it actually tells us something about the geologic history. Remember I told you how we had all of these terrains that were scrunching together and forming on each other? That creates volcanoes. So you get subduction zones, you get some material that's pushed down and pushed back up into volcanoes. The more quartz you have, the more felsic it is, the more light colored it is, the more explosive the volcano we're talking about. So this type of volcano would be equivalent to, say, Mount Vesuvius. So essentially what you're sitting on is a whole bunch of different Mount Vesuviuses over time. So this was just a huge complex of explosive volcanoes. Kind of makes you happy that we're living today and not, 300 million years ago. The darker the color, the darker the minerals themselves, if they have green in it. These are rocks that are more akin to what you would see coming out of Hawaii or Iceland. You can get some explosive volcanoes, but it's never on the order of what you see in felsic magmas. So we have a bit of a combination. Like I said, we have the Salem gabbro diorite. We also have the Capan granite. It's showing us that there's a transition, that there was mafic magma, so more flowing type of magma at one point, and then it changed. And this has to do with which terrains were actually intersecting with each other at which time, and how mature the rocks were that were being remelted when they were being crashed into each other. So it gives us a very detailed explanation of what was going on here in a very complex system. I'm going to throw this in. I won't spend too much time on explaining this, but this is essentially how we tell which minerals form first. Mafic minerals, so this is your olivine, pyroxene, all the dark colored or green colored minerals. These are really high temperature minerals. You have to have very high temperatures to have these in a melt. Once you get below a certain temperature, you can't form them. So the other way that you can also get volcanoes that are felsic is if you have a magma that sits for a very long time. Eventually it's going to cool off and you can no longer make mafic minerals. So not only do we have two different terrains that are crashing into each other, we're also having magma that's sitting there and the composition itself is altering because it's cooling off. It's really a fascinating story, and you get, if you're ever wondering what's going on when you see a couple of vans, usually from Smith College or Mount Holyoke that are on the side of the road at Capan, they're taking their petrology class out to look at what's going on there, because Capan is a really unique rock set that we have in New England. So quickly, I'm not sure that I have too much time to go through this, but where are all of these rocks being formed? Oh, they have to be coming from the core. No, the majority of rocks that we see in Capan actually formed right about here. So they're at the core, at the crust mantle boundary right about where the moho is. This is just a distinction between what is brittle and what is ductile. So this is actually where the majority of the rocks that make up Capan come from, is right here along this boundary. So they're not very deep. So we have fairly mature magmas that have created really complex systems. And that's what gives us what we have here today. Now, this tells you about how the rocks were formed. And if you go out and you can dig around, you might see places that have bedrock that are on the surface, but you also have a different part of the story going on. And that is, excuse me, that's what I was looking for. You also have a glacial history. So between 10 and 25,000 years ago, we actually had an ice sheet that was covering over a lot of North America. It's called the Laurentide Ice Sheet, named after Laurentia. It's not the same time period. Glacial history and geologic history are two different things. This was not the only time that the area has been glaciated, but it's the most recent glaciation. And that's what we have the remnants of that we can see. So this is just to give you an idea of how far down the Laurentide Ice Sheet went. This, excuse me, right there, that's the Chesapeake Bay. So New Jersey, and so the entirety of New England is covered over with this Laurentide Ice Sheet. Now, why is this important? Well, the petrology and the petrography that I gave you just before, that tells you about what rocks are here. But the glacial history actually tells you why they look the way that they do. So if you've ever been out hiking around Capan, gone on any of the trails, you'll see certain features like these crescent-shaped grooves within the rocks. These are actually glacial features, and they can tell you about which direction of flow that the glacier was going in. So the shallower side is kind of upstream, and the deeper side is the direction that it was going in. Another feature that you can see in some places, Pigeon Hill is a good example, is a drumlin or a roche montagne. But these drumlins show the direction of ice flow. So it kind of ramps up over this area, this rock or this collection of soils and sediments, and then essentially kind of gouges it out as it's going downhill. So you get these kind of shallow slopes on one side and steep slopes on the other side. If you've ever driven down Route 1, you kind of keep going up and down, up and down, up and down. It's a whole bunch of drumlins that you're just kind of going over in a line. This picture is not from Rockport. This is actually from Canada, but it's from the same time period that we're looking at, but it's a really great picture, and I couldn't find a good one from Rockport, which is unfortunate because I know that I've seen them. I just have never taken a picture of them, which now I'm going to have to do. Don't worry about these lines that you're seeing going across your screen. That's actually the rock fabric. So this is that's part of how the rock formed. What I want you to take a look at is these lines that are going kind of away from you on the screen vertically. Those are glacial striations. You can find them anywhere their glaciers were, anywhere in New England. You can look around and find them. People tend to think, oh, they must have had some sort of heavy equipment that scraped the rock. No, that's glacial striations. And they're everywhere. The other way that you can tell that we've had glaciers that have really changed the terrain is if you've ever tried to dig a hole anywhere in New England, especially in Capan, you've run into stuff that looks like this. And this is glacial till. It is a combination of boulders, cobbles, gravel, clay, sand, a whole bunch of stuff that nothing grows in. And that is glacial till. This is actually more sorted than I've ever seen glacial till, but if you ever dug in your backyard and figured out, why it's here, it's because of glaciers. So let me just give you a little kind of a background about how glaciers work and what other features that we see. And this is actually one of the things that I did not know because I had never seen this on the Babson Trail, but there is the word moraine there. If you've ever wondered about this word moraine, it's a glacial word. It is talking about the extent of a glacier. So when you have a glacier moving through an area, it's going to scrape everything off the ground itself and form a moraine. So that's where this term comes from. You can see ground moraines, you can see end moraines, but terminal moraines, this is the farthest extent that a glacier ever went. We do not have terminal moraines in Cape Ann because they actually went further down. The furthest extent of the most recent glaciation in New England that you can see in Massachusetts is Nantucket and Martha's Vineyard. They themselves are actual terminal moraines. That is where two lobes of the glacier actually met and created Martha's Vineyard and then Nantucket. Cape Cod is partially a terminal moraine as well, partially. So it's actually farther south than where we are today. But all of these features you can see in a lot of places in Cape Ann. Eskers are a little bit harder to find. These are underground rivers that have brought sediment out. They usually kind of make this sinuous kind of shape. You don't see them very much around here because they've all been kind of eradicated by human activity. Drumlins, we see quite frequently. We have moraine, we have kettles. So kettle ponds, if you've ever heard that term, that's essentially where ice has dropped off of the glacier and just sits and turns into a pond. They are also called vernal pools. So if you've heard of the term vernal pool, it's the same thing as a kettle. You go out to the Midwest, they call them kettles. Around here, we call them vernal pools. The reason why that they form and they kind of stay there is because of all of the clay that is coming off of this glacier that's being pushed around by this glacier. The clay acts as an aquitard, does not allow for water to go through. So the ice bits melt, they form this pond, and it takes a long time for that water to finally soak into the earth. And because of that, they're kind of they're seasonal. And this is essentially how glaciers work. You have till, you have all kinds of stuff that's being scraped along by the glacier. It's on top of the glacier, it's in the glacier, it's below the glacier, and it does not sort it out. So if you ever go to the beach, you can see sand that's usually the same size or gravel that's about the same size. If you go to a riverbed, you can see cobbles and that are about the same size. So we call that sorting when everything's about the same size or the same roundness. Glaciers don't do that. It just scrapes everything and drops it off. But it does lead to some interesting things, especially for Cape Ann, because the majority of this rock that has become kind of quintessential for Cape Ann, you know, the Cape Ann granite and so on and so forth, all of the quarrying that has gone on, it would essentially be under quite a bit of soil and sediment if the glaciers hadn't come through when they did. So most of this is visible because of those glaciers. This is a Pigeon Hill granite that you can see where they have the blocks that they're pulling out. If you look at Pigeon Hill itself is actually a drumlin. It is a glacial till drumlin. You can get glacial tills made out of rock. You essentially have the glacier that moves over the rock and scrapes it into this kind of teardrop shape. But you can get it out of a glacial till as well. And this is a picture or profile of a rock that is on Pigeon Hill that is more recently just in kind of the forest area. So if you're kind of going through Cape Ann, there are a number of different places that you can go and you can see these features themselves. One other feature that I didn't mention that you can see that are related to glaciers are glacial erratics. So you might have heard the term erratic being talked about with these large boulders. This is from the Briar Swamp trail. You see glacial erratics here. If you look over in the right-hand photo, you can see all these rocks kind of sticking out, and they're pretty much everywhere. And it's because the rocks are so close to the surface. You have lots of different size rocks. Some of them are glacial erratics, some of them are just till, and they go everywhere. Now, I did mention earlier on that the topography was interesting because you can see from these contour lines, we have some lines that are closer together. This means that you have a steeper slope. Anywhere that you have kind of like a bullseye kind of feature, that means that you're talking about like a hill. And you can kind of see these lines that kind of follow each other. These are all glacial features. These are moraines. These are drumlins, and they are indicative of the glacial terrain that we're seeing today. And this is actually one of my favorites. I'm sorry, I didn't do this one correctly. had meant to make that kind of fly in. This is excuse me, this is Dogtown. This is a map of Dogtown, and I just pulled up all of the different features that you can see in Dogtown itself. So you have Granny Day Swamp, you have Briar Swamp. These are kettles that have filled in and are now swamp-like. You have the gravel pit, this is Glacial Till, and then you have Peter's Pulpit and Whale's Jaw. These are Glacial Erratics. So the majority of what we see across Capan is related to the glacial activity, but the rocks that were there are far more ancient than we can even kind of wrap our heads around, really. And I'll leave you with this wonderful picture of all the glacial erratics that you can see near Dogtown Commons with the piggery that they had in the early 1900s. So I do
terrific, Kate. We have a couple of questions in the chat.
Sure.
One is, how does the geology of Cape Ann provide resilience or vulnerability to climate change and global warming?
So because you have so much rock and not as much sandy beaches, which some people like, some people don't, rock is more resistant essentially to weathering away. So you can think of places like the Bahamas or Florida that have to deal with a lot of sand that's going, or even Newburyport. You hear about Plum Island all the time having to deal with all of the coastal erosion. Rockport's a little more protected from that. As far as sea level rise, that goes along with climate change. The marshes are going to be underwater eventually, and that's going to start affecting any of the houses that are there. But it's a little bit better, but it's still going to be an issue that we have to deal with one way or the other.
When was Cape Ann last submerged or connected by land to the mainland?
As Pangea? Probably, I would assume. So the last time that it was connected was about 200 million years ago. So this was a connection between essentially Cape Ann, England, and Africa.
Terrific. And given our geology, what is the short-term stability of our groundwater?
So that is a different conversation to have entirely, and I could talk probably about an hour and a half on that one.
We'll bring you back for that one. I've got another question. What about the
quick answer?
Sorry, go ahead.
The quick answer is that we have lots of fracture networks, which is actually great for groundwater. The problem is that it takes a long time to infiltrate in. So if you have to worry about things like wells, if you manage it correctly, it should be okay. But I say this very seriously. The problem is not so much getting the water out. The problem is making sure it's clean. And that's the bigger question. So go ahead, Dana, sorry.
I've got another question in the chat. What about the over 300 mafic dikes on Cape Ann?
So those are about the same age as when the when the Cape Ann granite complex was in place. So they seem to be about the same age. Everything seems to be about Ordovician in age. So you had a really complex set of situations where you had several smaller microcontinents that were converging together, and they created the Salem Gabbro Diorite, the Cape Ann granite complex, and then also these mafic dikes as well that were going through. The most recent thing that I've read about them is that they think that they originated from the same source that the Salem Gabbro Diorite originated from, but they're basaltic, not gabbro, which tells you that they cooled closer to the surface. So however that that magma formed, the gabbro was much deeper down, took a longer time to cool. The basalt was closer to the surface and cooled quicker.
Any other questions for Kate? If anybody thinks of any questions, you can certainly send them to me and I will send them to Kate. Oh, one other. The dikes range in age from Mesozoic to about Devonian. That was in response to what about the over 300 mafic dikes on Cape Ann?
So Mesozoic is during Pangea, and So that would be when Pangea was breaking apart. If you're talking about the ones that are inland, we're talking about the ones that are Ordovician Devonian age. If you're talking ones that are on the edge, that are essentially when Pangea broke apart, that's why that they're there.
Kate, this has been incredible that you've covered almost 1 billion years in 45 minutes. I have to say, that may be a record.
I try. All right.
Well, thank you. I recognize that you need to leave and
Thank
I
you.
see no other questions. But again, if anybody has questions, you know where to reach me. I will make this available on the YouTube channel for the library within the next few days. And I thank everybody, but especially thank you, Kate, for always coming to our rescue with wonderful science topics and especially local. So
Absolutely.
thank you so
Absolutely.
much.
All
Thank you
right.
very
Have a
much.
good night. Thank you.
Thank you, everybody. Thank you, Kate. Good
Bye-bye.
night.